Floris will talk to us about some technical.
Is this readable now, the slides? Okay. First of all, I would like to thank the organizers very much for providing the Zoom stream. I've been sick for a lot of this conference, and I'm very happy that I could attend this conference remotely when not feeling great. But for now, I'm feeling better, and I want to give you a little bit of a demo of some lean. Not sure what the influence.
You haven't come across that before, yeah, try one more time.
Okay. Okay, I'll try it a little bit more. Hopefully it works. Is the microphone still working? Yeah, okay. Yeah, so I want to do a little bit of a lean demo showing off like some of the meta-programming capabilities lean has, and some like maybe some problems or limitations of lean and how we're trying to resolve them with like some of lean's meta-programming. With some tactics I've been working on. So this file is online, and if you want to run it yourself, there's a script in Mavlib called makeall, which creates a file which imports all of Mavlib. So this is actually a file which has imported every file in Mavlib.
I haven't been able. I haven't posted it on the web page yet.
Okay.
It's on the Zula. I did post it to Zula.
It's this file or a version of this file is on Zulip. So this first thing I want to talk about is something we call localized notation. So in Lean, there are two ways to define notation. So if you write something like this, you write global notation, and now in every file which imports this line, you have the notation that omega is like the cardinal omega, which is maybe not what you want. Like maybe you want sometimes omega to be the ordinal omega, or just some very different definition. So there's another method you can write local notation, and now this omega is local just to this section. So if I'm outside this, so now I'm inside this section, and if I also write print omega, it tells me on the right, like omega is notation for kernel omega, but if I'm doing that here, then I get an error like omega doesn't exist. So this is sometimes what you want, but this results in certain local notations to be defined many times over, because certain notations you don't want globally, but you want many times in different files. For example, every time you might work with cardinal numbers, you might want this notation. So with the meta-programming language, we have a new thing called localized notation, which is sort of in between. And the syntax is as follows. So instead of local, you write localized, and you put the notation command in quotes. That is currently just a limitation of the parser, that it's easier to parse a string and not so easy to parse exactly the notation command. Of course, in something like Lean 4, we could make this notation easier. And we put this notation in something we call locale. In this case, we call it cardinal. So what this does is two things. So for it declares the local notation right here, and it's local. So at the end of the section, it's gone. But now, if you want in a new section or in a new file notation again, what you can do is open the locale cardinal, and then it's every notation you've declared, like in this locale cardinal, you get is locally declared again. So now omega is for in that section is defined again, and outside the section it still doesn't exist. So this is a feature we use to like declare notation which we want in some namespaces or in some areas of math, but not in always. And so you can also run a command, this one, which declares like all the localized commands in a particular locale. So currently in the cardinal locale, there's one which we just declared, the cardinal omega, and there's a cardinal.make, which is declared in some other file in mathlib. So yeah, this is one thing. And so, for example, there's an open locale classical, which certain people have used, and then you get like the property that all propositions are decidable as an instance. I have a time next to me, so I know how I'm doing on time. So this is one instance of like something which is purely done with metaprogramming. So all of this doesn't touch the C++ code base. It's purely done in metaprogramming. So here's another example of a tactic done in metaprogramming. Suppose we have this problem. So we have the rational number n, and we know that the denominator of n is equal to 1. And then we want to prove some property about n, which is true for integers, because like the property of the number 1 sort of says that n is an integer. This is like an instant kind of problem where you have an object in one type, but you really want to treat it as an object of another type because some property holds. And so there's a nice tactic called lift. So you can say lift n to the integers. So yeah, so before, so this is the Lint's goal state if in tactic mode before I do the tactic, and then if I run the tactic, it has now transformed the the rational number n to the integers, and proves I'm required to prove the same thing. So the up arrow is a coercion which turns into a natural number, into a rational number. And then there's a second goal which shows that I exactly have to prove that the denominator of n is 1, which is the requirement for some rational number to lift to the integers. Or I can discharge that goal immediately by saying lift n to the integers using the extra hypothesis Hn. And then it actually also removes the hypothesis Hm from the context because now that's superfluous. And now this is a property about integers which I can prove. So, so there's a nice tactic called normcast, which allows you to, if you're working with coercions, it sort of tries to simplify all the coercions in expressions. So now this normcast tactic actually has transformed the goal, instead of using inequalities on the rationals, into inequalities of integers. And now this looks like something that's in the library, but of course we don't know what this property is called. I mean, we could guess, but there's also nice tactic Librarysearch. I've imported all, so, and indeed, Librarysearch, after thinking for a bit, has told me that the way to solve this goal is this tactic. So currently you just have to manually copy paste it. And so then I've solved the goal. So this is displaying like some of the tactics which have all been added over the last year, I think. So the lift tactic, normcast tactic, and the Librarysearch. Yeah?
What happens if we put assumption n in integer?
If you put assumption?
N is an integer, not pure.
Oh yeah, so so if we just start with n as an integer, then of course we don't have to lift it to the integer. So the first line is like to allows you, so if something is sort of inconveniently in the wrong type or something, then you can lift it to like where you would expect it. And this occurs quite frequently, like you might have an integer and you know that it's non-negative, then you really want to treat it just as a natural number. Yeah?
So does this lift technique have to have some setup?
Yes, there's a little bit of setup. So, yes, so what you need to do is there's a structure which is called can lift. I don't know how well, so you need to provide an instance of this structure. Let's see. Yeah, we can go to the definition. So, so this is a class which allows you to be to lift elements from the first type alpha to the second type beta, assuming that some condition is true. So for this, you need three things. You need a map from beta to alpha. So in our case, we need a map from the integers to the rationals. We need a condition on alpha. So we need a condition on the rationals for it to like allow it to lift. And then you need to prove that if the condition is true for some element in alpha, then there exists an element in beta. So there exists an integer which is turned into the rational number. And so for the example we had to like explicitly give like an instance with the fields for the rational number. So currently these are the ones defined in mavlib. So there's a can lift instance from the rationals to the integers, which and inside it tells you what the condition is that you have to prove. And so here I had a little example. So for example, we can add an instance which allows us to lift from any type alpha to a subtype of it, of some property, property P. And so we need to give three things. We need to give a map from the subtype of P, the subtype of alpha to alpha itself, and there's a coercion which does that. We need secondly a condition. We need a condition for an element in alpha, which is necessary to lift it to the subtype, which is just P. And in this case, we need a proof that if the condition is true, then we get an element in the subtype, which is this thing I had written here. And then here's sort of a contrived example. So suppose we have an element like x plus x, an assumption that x plus x is greater than or equal to 0, and for some reason we want to lift it to like the non-negative reals. We can now do it. We can say lift x plus x to the non-negative reals. So let me just first write this. So now this looks kind of ugly. So first of all, I need to prove the assumption that x plus x is greater or equal to 0. So I can just write using h, which is the proof of that. And now it generates a new variable of the subtype I have. And I can give it, give the new variables a name, for example, with y and hy. And so now y is the new variable in my subtype, and hy is the proof that the first projection of that element is indeed x plus x. Here, because we're not lifting a variable but an actual term, we cannot like substitute away the x plus x everywhere. And I mean, this is kind of a contrived example because I don't think this helps in actually solving the goal. But yeah, there are probably cases where you want to like lift to a subtype or more generally lift from one type to another. Any other questions? So another thing which I recently added was the Simps Attributes. So this is currently used mainly in category theory, but also in other places. This problem, the problem which this attribute is trying to solve is, suppose we define some element of a structure. So, for example, we here have the composition of two functors. So I have two functors f and g, and we want to define the composition of those two functors. And we define it by saying what it does on objects, saying what it does on maps, and actually, because the category theory library is set up very nicely, Lean will automatically use automation to prove that the other two fields of a functor, showing that it's exactly a functor. And what we want for these kinds of definitions is that we want to know what the components are. We want to know that the object part, if we have this in an expression, like the composition of f and g and then the objects part, we want it to reduce to whatever we have defined here. And like the simplifier of Lean is a good way to do that. So one thing we can do is just write the attribute simp here, and that just tells Lean, whenever you see this definition anywhere in my goal, and you call simp, just unfold this definition. But that's not always what you want, because if I just have the composition of f and g in my goal and no projection, then probably I just want to keep the composition of f and g in my goal. Only if I want to, if I explicitly extract like either the object part or the map part of it, I want to like unfold this definition. And so that's what the Simps attribute does. What it does is, if I add this attribute, it generates automatically two new lemmas. It's currently compiling the definition. They are not too readable, but so the important part is, because all the arguments are explicit now, so the important part is this. So it says that if I take the object part of my composition of f and g and apply it to an object x, then it's exactly what I defined on this line right here. So it automatically generates lemma like the first projection or the second projection of the instance of a structure I just defined is equal to whatever I defined it as. And it automatically marks it as a simp lemma. So whenever you call simp and you have something in your goal of this form, it automatically replaces the thing on the right. Nice. And it works on more complicated things. For example, if you do, okay. So here, so it also does like nested. If you have nested structures, for example, here I have an object. So I have the associator with product categories, and then it's like you can configure whether it's it just applies a single projection or it's like applies like projections as deeply as it can, because sometimes you want one, sometimes you want the other. Yeah, let me move to the last thing I want to talk about, which is the linter, which has already been mentioned earlier in, well, at least yesterday. So the linter is a nice command which I worked on, and Rob also improved it, which sort of tries to find some semantic problems a definition can have. So you just call it by writing #lint, and it will by default will just check whatever you have in your current file. So it says, well, there are 7 declarations in the current file so far, which I checked, and it says, well, most tests turned out okay, but actually you wrote 2 definitions in your file which you didn't write documentation strings for. And in Mavlib, we want all the definitions at least to have documentation strings. So, well, I can quickly say this is my associator. It doesn't check the quality of documentation strings. Yeah. And so now it only says that my composition is missing the documentation string, but not the other one. You can also lint all of Mavlib. So for example, here I'm linting in Mavlib for all declarations, only a single linter, namely whether a declaration is using, has any unused arguments. And then you get a list. So it says, well, first of all, interestingly, there are just over 30,000 declarations in Mavlib.
Excluding a lot of them.
This is excluding a lot of automatically generated declarations. Type recursions you get for free, and it doesn't lint all of those. And as you can see, there's still a bunch of examples in Mavlib, declarations in Mavlib where it still has unused arguments, and we still need to go. Yep, exactly. For p-edit sec. So yeah, so we still need to do the actual cleanup, but this is a nice tool to find like common mistakes in formalization. And there's also a command which lists all the linters which are currently available. So this is the current set of available linters. So you can check for unused arguments. You can check whether a namespace is duplicating a name. That is sometimes a problem. You call a theorem like lattice dot my theorem, and then you put it later in the namespace lattice, and now the name is lattice dot my theorem. And then there's this doc blame, which is checking whether things have doc strings. Then there's sort of illegal constants, which is kind of like constants which we don't want in theorem statements, checking whether something is correctly declared as either a definition or a lemma, and something about instance hygiene, that it doesn't have a too large priority for instances that always apply. Yeah?
About illegal constants, what is the current status of not allowing greater than equal except if it's for all?
Yeah, so currently, for example, we indeed don't allow greater than or equal in theorem statements because it's defined to be less than or equal, but it's inconvenient to have like a theorem which uses greater than equal. You want to apply it when you're talking about less than or equal. I think we should indeed relax that condition to allow it in certain cases where you, for example, quantify over all epsilon greater than 0 or something. It's not yet done. Yeah. Yeah, and so it's not that hard to write your own linter. Like some of the linters are just like 5 lines of code to write your own linter and add it to the lint set. So there's still like some suggestions of other linters we want to add. Yeah, and then of course we also have to manually go through the library to fix all the mistakes, but like knowing that there are mistakes is half of the work. So these were some of the things I wanted to show about like what you can do with Lean's metaprogramming. Yeah, thanks.
Time for a few short questions.
Oh yeah, so all the tactics and commands are documented in Mavlib. There's in Mavlib in the folder docs. There's like a tactics file which.
It's no longer the best source.
Oh yes, oh yeah, yeah. Where?
On the screen.
Hmm?
I haven't been projected yet.
So this is lean prover. This one. Now API documentation. Now can I go somewhere to tactics? Yeah. So this one maybe a little too quick. So this is the lean prover community website of Mavlib. leanprovercommunity.github.io, and Rob made like a nice documentation of all of Mavlib, which you can view in HTML. And then here there's a table of contents. You can go to tactics, and this is all the documentation of all the tactics in Mavlib, which have documentation, which is almost all of them.
Some of the things
So-
Floris showed, like the localized notation in commands, so right under tactics.
Yeah. So for example, if I go to the linter, so here's the documentation for the lint command.
They get generated from the doc files in Matplotlib.
So you're just in all of Matplotlib and putting it on one page?
No, there are files in the doc directory of Matplotlib.
Oh, this is the
Yeah.
end.
I mean, they're processed, right? So they're sorted by tactic name, etc.
But
They're
there's
being
also
extracted.
there's also document collected in other places.
I didn't see the nice organization of the tactics yet, but that's nice.
Right before Christmas.
Okay.
Thank you, Rob.
Yeah.
Other questions?
I have just a small question about the localized notation. You know, is it possible to locally cancel a global notation?
No, it's possible to locally declare a notation which overrides the global notation, but I don't think Lean offers the functionality to indeed remove like global notation, which is sometimes annoying.
But I can override a global notation to just be equal to itself.
Yeah, yes. Yeah.
Well, you see, if you remember my talk, I was using the boldface Q for something that's not wrapped. And that used to be okay, but something changed in Matplotlib. The wrap was important.
That should pop up in the local location order open field, and it only what you say, and not wrap.
Yeah.
Locales are just notations or any definitions?
So currently we only use it for notations and attributes.
Locales and physical, of course, are very different.
Yeah. Yeah, but we also, we needed some name.
Oh, maybe, yeah.
We could use it. Oh, how do you mean for, and then, I guess.
So first of all, these are some very nice examples. For the localized in particular, so for before we were planning to put notations inside namespaces, make them good by default. Maybe no duty there if you open the namespace before. Is that uncover all of the localized use cases, right?
It's,
We want to be able to add theorems in another namespace, so it's still using the local notation. And you would be forced to correlate all.
If you don't want definitions inside the same namespace as the notation, like you only want the notations and not other things, you should put the notations inside a separate namespace, which I think is really equivalent to taking up a completely new thing like a locale. You just have a new namespace.
No, but for instance, if I'm doing a topology and we've got a topological space namespace and a uniform space namespace, but some of the things on topological space I need some notation, and but I want my new theorems to be added to uniform space namespace, but still use notation from the topological space.
Yeah, if you open the namespace and then the notation shows up, you don't have to be inside the namespace.
Ah, you don't have to be inside.
Yes.
Okay. Sorry, I was.
It has to be open.
Okay.
Yeah, I think that would be a big improvement to the current status.
Another thing the localized stuff is used for is type class instances. So some of the classical instances that we don't want to be global instances are in the classical locale. So open locale classical, open the namespace, gives you a few of these instances.
Yeah. Yes. Of course, that was exactly what we could feature that made us do.
Yes.
Yeah.
I mean,
Yeah.
this I think pretty obviously should not be tied to a.
Yeah, and it's not by default.
Okay, next.